The steady-state model of the universe was first proposed by two Austrian-born British astronomers, Hermann Bondi and Thomas Gold, in 1948. It was further elaborated by Fred Hoyle and other cosmologists of repute. The universe, according to this idea, has always existed. It has no origin and will continue to exist indefinitely. Even though the universe is expanding, it maintains its own average density, or steady state, by constantly creating new matter. Several cosmologists today reject this model because it does not accommodate background radiation, or the fact that the universe's appearance fluctuates over time. The steady-state model of the universe was influenced by a film from the 1940s called Dead of Night. The movie was divided into 4 categories and presented a circular structure such that the ending was similar to the beginning. Following their viewing of this film in 1946, Hermann Bondi, Thomas Gold, and Fred Hoyle questioned if the universe was formed in the same fashion. The debate that ensued eventually led to the steady-state hypothesis. In cosmology, the steady-state model believes that the universe is constantly expanding while keeping a steady average density. It also elaborates that matter is constantly being created to give shape to new stars and galaxies at about the same rate that old astronomical objects become invisible due to their progressive distance and rate of the downturn. A steady-state universe has no origin or endpoint in space. Besides, the perspective on the grand scale, that is, the average density and organization of galaxies, are identical from any location from inside. Galaxies of all eras are merged. Sir Hermann Bondi, Thomas Gold, and Sir Fred Hoyle, all British scientists, first proposed the model in 1948. Hoyle expanded on it to address issues that had surfaced in terms of the alternate Big Bang theory. Since the 1950s, several studies, especially those of the cosmic microwave aspect, anticipated by the Big Bang model, have produced abundant data contradicting the steady-state image, leading scientists to accept the Big Bang hypothesis decisively. Steady-state model and other unconventional cosmologies. Despite the bottlenecks, almost all astronomers favor Big Bang cosmology, which is amplified by inflationary ideas. However, no consensus has emerged on the roots inside the cosmic gas of the volatility ideas to produce the apparent galaxies, clusters, and superclusters. The majority of astronomers would view these flaws as evidence of the incomplete maturation of the model. Still, there may be scope for significant changes. The seemingly significant gap between the Hubble time and other measures of cosmic age was an early difficulty faced by Big Bang proponents. Hubble's initial figure for H0 was about an indication of the high magnitude due to skepticism between population 1 and 2 changeable stars and between H2 territories and bright stars. This imbalance was resolved by revising Hubble's initial estimate for H0. In 1948, Bondi, Hoyle, and Gold proposed an alternate theory of the steady-state model of the universe in response to the apparent problem. The universe was believed to be expanding by that year. Therefore, the only way of explaining a constant, steady-state matter density was to hypothesize the ongoing creation of matter to compensate for the cosmic expansion's retardation. Numerous people found this part physically unattractive, knowingly or unknowingly, preferring to complete all creation in almost one instant in the Big Bang sphere. According to the steady-state model, the average age of matter in the universe is equivalent to 1/3 of Hubble time. However, any galaxy could be older or younger than this average figure. As a result, the steady-state theory had the advantage of making precise predictions, but it was sensitive to observable disproof. Counts of extragalactic radio emissions by British astronomer Martin Ryle in the 1950s and 1960s struck the first blow. These counts employed the same procedures used by Dutch astronomer Jacobus Kapitein to count stars and Hubble to enumerate galaxies. Here, only radio telescopes had been used. Whether the cosmological model was adopted, even that of steady state, Ryle discovered more radio galaxies at enormous distances from Earth than can be justified by the premise of a uniform geographical distribution. It appeared to suggest that radio galaxies must evolve with time, and with more strong sources existing in the past, observable at greater distance, than there are now. A core principle of the steady-state model states that all large-scale attributes of the universe, including the population of any subclass of objects like radio galaxies, must be consistent throughout time. The disclosure of the identification of cosmic microwave background radiation in 1965 dealt the second blow. The steady-state model is credited with being a compelling solution for the rise of modern cosmological thought, because it spurred considerable study in the subject, even though it has limited followers today. Numerous different alternative theories, such as the cold Big Bang theory, to contribute to galaxy formation, symmetric matter-antimatter cosmology, to prevent an asymmetry between matter and antimatter, variable G cosmology, to help illustrate why the gravitational constant is so modest, tired light cosmology, to clarify redshift, and the presumption of receding atoms in a non-expanding cosmos, have all been proposed as obstacles to the contemporary view of the origin of the universe in a warm scenario, to avoid the individuality of the Big Bang. As noted in the parenthetical notes, the objective behind these proposals is to correct a perceived flaw in the standard image. However, in the vast majority of situations, the solution suggested is worse than the ailment, and none of the alternatives mentioned have gained much traction. The popular Big Bang theory has risen to prominence because, unlike its many opponents, it aims to address a wide range of cosmological difficulties rather than a few isolated facts. And while some desired outcomes are still elusive, no obvious weaknesses have yet been discovered. In the 1950s, the steady-state model was immensely popular. During the early 1960s, however, arguments contradicting the notion began to emerge. For starters, observations made using radio telescopes revealed that there had been more radio emitters far away from humans than the theory expected. People may presume billions of light years when they say a big distance, because of the time it takes light to reach the Earth. People are looking back billions of years in time when they think of objects billions of light years away. So these findings indicate that billions of years back, there were more cosmic radio sources than the present time. This counters the steady-state paradigm by implying the universe is evolving throughout time. In 1963, a new group of astronomical objects known as quasars was found, providing much more evidence to disprove the idea. These are extremely luminous objects that can be 1,000 times brighter than the Milky Way, yet are extremely small compared to the size of a galaxy. Quasars can only be found at considerable distances from Earth, implying that their light was discharged billions of years ago. The fact that quasars have only been discovered in the early universe is strong proof that the cosmos has evolved throughout time. Steady-state model of the universe. An overview. The steady-state model is a cosmological alternative to the Big Bang theory of universal evolution. The density of matter in the expanding universe remains intact in the steady-state model due to the continual creation of matter, conforming to the pristine cosmological principle which states that the observable universe is nearly the same at any given time and place. While the steady-state model had some backing in the scholarly mainstream until the mid-20th century, the large bulk of cosmologists, astronomers, and astrophysicists now dismiss it because observational indicators point to a hot astrophysics with a discrete age of the universe, which the steady-state model does not foretell. Background. Sigurd of Brabant wrote The Eternity of the World in the 13th century, claiming that there was no first human and no first specimen of any specific instance. The physical cosmos is thus everlasting, because it has no origin. In 1277, the Pope criticized Sigurd's beliefs. Edwin Hubble's observations led to the discovery of cosmological expansion. The static universe modeled by Einstein, 1917, was equally fragile, according to numerical simulations. As per the contemporary Big Bang theory, the universe has a limited age and has evolved through expansion, cooling, and gravitational compression to form structures. The steady-state model claims that given that the universe is expanding, its shape does not change over time, the ideal cosmological postulate. The universe has no origin and no end. It necessitated the creation of new matter continuously to keep the universe's density from dwindling. In 1948, Hermann Bondi, Thomas Gold, and Fred Hoyle released influential studies on steady-state cosmologies. William Duncan Macmillan, among others, has presented similar theories in the past. Many years before Hoyle, Bondi, and Gold, Albert Einstein contemplated a steady-state model of the expanding cosmos, as shown in a 1931 paper. He abruptly abandoned the plan, though. Observations. Issues with the steady-state model emerged in the 1950s and 1960s when astronomical assertions started to support the concept that the universe was evolving. Bright radio sources, radio galaxies, and quasars were discovered only at greater distances, and thus could have only emerged in the distant past, not in nearby galaxies. Unlike the Big Bang hypothesis, which predicted that such objects would be discovered throughout the cosmos, even close to the galaxy, the steady-state model projected that such objects would be located throughout the universe. By 1961, most cosmologists believed that statistical analysis based on radio source surveys had ruled out the steady-state model. However, some proponents of the steady-state model were of the view that the radio data were questionable. The finding of the cosmic microwave background radiation, which was projected by the Big Bang hypothesis, provided a convincing rebuttal of the steady-state model for most cosmologists in 1964. The steady-state hypothesis interpreted microwave background radiation as light from primordial stars fragmented by cosmic dust. The cosmic microwave background level, on the other hand, is very consistent in all orientations, making it more difficult to illustrate how a large number of point sources could have generated it. Also, the microwave background radiation provides no sign of dispersion characteristics, such as polarization. Moreover, its spectrum is so similar to that of an optimal black body that it could not have been created by the superposition of inputs from a large number of dust clumps at various temperatures and redshifts. The steady-state model does not appear to correspond with the observable dl versus z connection, or with source populations. Steven Weinberg so noted it in 1972. In some ways, this discrepancy is a complement to the model. It is the only cosmology that makes precise predictions that can be refuted even with the minimal empirical evidence. The steady-state concept is so appealing that many of its proponents still believe that as observations develop, the arguments against it will fade away. Though the universal microwave radiation is truly black body radiation, it will be difficult to deny that the universe has originated from a hotter, denser, primitive stage. The Big Bang scenario has been regarded as the best description of the universe's genesis since its discovery. The Big Bang is tacitly accepted in most astrophysical papers and is used as the foundation for more detailed hypotheses. Quasi-Steady-State. Fred Hoyle, Jeffrey Burbidge, and Janet V. Narlicker suggested quasi-steady-state cosmology, QSS, in 1993 as a new iteration of steady-state notions aimed to explain extra aspects not addressed by in the previous approach. According to the model, mini-bangs, mini-creation events, or little bangs, are areas of creation that happen with time within the universe. Further changes to the concept were made with the discovery of an expanding universe. The Planck particle is a speculative black hole with a Schwarzschild radius roughly equal to its Compton wavelength. Its dissipation has been suggested as a source of light elements in a progressive steady-state universe. The model has shortcomings, according to cosmologist and astrophysicist Ned Wright. The proponents quickly countered these initial remarks. Wright and other conventional cosmologists who reviewed QSS have discovered fresh problems and conflicts with findings that proponents have left unresolved. Steady-state model of the universe, a phase-wise account. A variety of models have been proposed throughout history about cosmic origins. Every civilization has ever lived in a mythological legacy that accommodated a creation narrative by default. Cosmologists and scientists began to interpret the universe concerning physical postulates that could be tested and evaluated with the advent of the scientific tradition. Scientists began testing cosmological hypotheses in terms of observable occurrences with the advent of the space age. As a result of all of these happenings, and by the second half of the 20th century, several ideas had emerged that claimed to explain how all substance and the physical laws that govern these events had surfaced. The Big Bang theory is the most commonly accepted ideology, whereas the steady-state model has long been its strongest rival. According to the steady-state model, the density of matter in the growing cosmos remains constant across time due to the constant matter formation. To put it another way, independent of time or place, the observable universe remains relatively the same. This contradicts the popular belief that the bulk of matter is produced in a single event, the Big Bang postulate, and has been evolving ever since. Genesis. While the concept of a steady and everlasting universe has been acknowledged throughout civilization, scientists did not begin to interpret it in an astrophysical dimension until the arrival of the early modern age. Isaac Newton's mathematical principles of natural philosophy, Philosophiae Naturalis Principia Mathematica, scripted in 1687, was the very first notable example of this being discussed in the framework of both astronomy and cosmology. In his magnum opus, Newton envisioned the universe far beyond solar system as a void that spread equally in all directions to incalculable distances. He further demonstrated that the solitary principle of universal gravitation described all motion and dynamics in this structure through mathematical formalism and observations. But it wasn't until the early 20th century that the steady-state model of the universe was proposed. A multitude of scientific advancements and discoveries in the realm of theoretical physics prompted this cosmological model. The theory of general relativity by Albert Einstein and Edward Hubble's findings that the universe is expanding was among them. By 1915, Einstein had formulated his theory after deciding to add gravity into his special relativity hypothesis. Eventually, the gravitational pull of matter and energy affects the curvature of space-time around it, according to this concept. Space-time instructs matter how to move. Matter directs space-time how to curve, as renowned theoretical physicist John Wheeler explained. By 1917, theoretical studies based on Einstein's field equations revealed that the universe had to expand or contract. By 1929, observations made by Georges Lemaître, the proponent of Big Bang theory, and Edwin Hubble, employing the Mount Wilson Observatory's 100-inch Hooker telescope, had established that the latter might have been the case. Founded on these insights, a debate concerning the universe's potential beginnings and fundamental nature sparked up in the 1930s. Contrarily, some scholars claimed that the universe was bounded by age, and that it evolved through the cooling process, expansions, and the emergence of structures owing to gravitational pull. Fred Hoyle derisively dubbed this notion the Big Bang, and the label remained like that. Furthermore, the bulk of astronomers at the time believed that, while the visible universe was expanding, the density of matter did not fluctuate. In a nutshell, proponents of this theory claimed that the universe had no origin or end, and that matter was continually generated over time. It was moving at the rate of about 1 hydrogen atom per cubic meter each 100 billion years. Einstein's cosmological criterion, commonly known as the cosmological constant, CC, which he suggested in 1931, was also backed up by this hypothesis. The component, according to Einstein, was required for restricting gravity and assuring that the universe's large-scale structure remained relatively stable, uniform, and isotropic. Advocates of the steady-state school of thought modified and expanded this idea, arguing that the constant creation of matter meant that the universe's structure stayed the same across time. The ideal cosmological theory, which underpins the steady-state model, is also recognized in the same way. With the addition of 2 reports in 1948, the steady-state model had widespread recognition. The papers were popularly known as A New Model for an Expanding Universe, presented by English astronomer Fred Hoyle, and The Steady-State Theory and the Expanding Universe, scripted by Hermann Bondi and Thomas Gold, both British-Austrian astrophysicists and a cosmologist team. Predictions and Key Arguments. The potential time-scale dilemma, highlighted by the known rate of cosmic expansion, is one of the arguments in favor of the steady-state model, the Hubble-Lemaitre law, or the Hubble constant. Hubble concluded that the universe was expanding at a rate that grew predictably with distance. It was premised on his observations of neighboring galaxies. The theory that the universe began growing from a considerably smaller region of space came about due to this development. The Hubble constant in the absence of acceleration or deceleration minus 500 kilometers per second per megaparsec, 310 MPs per MPC, implied that all matter had been expanding for around 2 billion years, which would also be the universe's maximum age. Radioactive dating, which evaluated the mutation rate for deposits of uranium-238 and plutonium-205 in sediment cores, refuted this inference. The oldest samples of rock from the Moon were calculated to be 4.6 billion years old, and this approach was corroborated. Following the stellar evolution theory, another incongruity evolved. To summarize, the pace at which oxygen is fused in the center of stars to form helium gives globular clusters, the galaxy's oldest stars, an upper age range of 10 billion years. Besides, there might have been no evolution in this concept at long distances, implying that radio emissions, also known as active galactic nuclei, AGNs, or quasars, would be homogeneous throughout the universe. The Hubble constant, as determined in the early 20th century, would also stay unchanged. The steady-state model also anticipated that regular annihilations and neutron disintegration would follow from the constant generation of antimatter and neutrons, resulting in a gamma-ray baseline and hot X-ray producing gas across the universe. Big Bang impact. Observations throughout the 1950s and 1960s, on the other hand, gradually accumulated evidence opposing the steady-state model. These observations included detecting powerful radio objects, also known as radio galaxies and quasars, in distant galaxies, but not in galaxies closer to Earth, implying that many galaxies turned radio quiet over time. By 1961, studies of radio sources had encouraged deep statistical analysis, ruling out the eventuality of evenly distributed luminous radio galaxies. The revelation of the cosmic microwave background, CBM, in 1964 that predicted the Big Bang model was another central issue against the steady-state model. By the 1960s, the Big Bang hypothesis had gained widespread acceptance due to the lack of a gamma-ray background and extensive clouds of X-ray producing gas. Observations with the Hubble Space Telescope and other observatories in the 1990s have revealed that cosmic expansion has not been uniform over time. In fact, it has accelerated during the last 3 billion years. The Hubble constant has been refined as a result of this development. The rate of cosmic expansion is now predicted to be between 70 and 73.8 kilometers per second per MPC, or 43.5 to 46 MPs per MPC, based on information gathered by the Wilkinson Microwave Anisotropy Probe, WMAP, with a 3% margin of uncertainty. These figures are far more in line with the data that put the universe's age at roughly 13.8 billion years. Variance in modern times. Commencing in 1993, Fred Hoyle, Geoffrey Burbidge, and Janet V. Narlikar, astrophysicists, and other cosmologists, suggested a new version of the steady-state model in a series of papers. This modification, dubbed as the Quasi-Steady-State hypothesis, QSS, aimed to explain cosmological occurrences that the original theory failed to prove. This hypothesis proposes that the universe was formed over billions of years by pockets of creation, also known as mini-bangs. The model was modified in response to findings indicating that the pace of expansion of the universe is speeding up. Despite these modifications, the astronomical community still considers the Big Bang the best model for explaining all observable phenomenon. The lambda cold dark matter, LCDM, model, which merges contemporary hypotheses about dark energy and dark matter corresponding to the Big Bang theory, is the name given to this reference model. Considering this, some astrophysicists and cosmologists continue to support the steady-state model and related variants. It isn't the only option to Big Bang cosmology either. Steady-state model of the universe. Arguments for and against. The steady-state theory has many flaws, but it did have certain advantages when it was first introduced. The perfect cosmological postulate is the foundation of the steady-state model. Consequently, any evidence that the cosmos evolves is ample proof that the steady-state theory is inaccurate. The existence of quasars and the variation in the expansion rate of the cosmos a few billion years ago provides enough indications that the universe is not in a stable state. When the steady-state model was first proposed in 1948, there was no trace of the universe's evolution. By the mid-1960s, it had become an integral part of the growing body of data stacked against the steady-state hypothesis. Defenders of the steady-state concept, notably Hoyle and Janet Narlikar, have claimed that the cosmos can transform over a few billion years without breaking the ideal cosmological principle in valiant endeavors to save it. To see if these fluctuations average out, one needs to consider even extended periods. The death punch to the steady-state model is usually seen as cosmic background radiation. In the wake of what most astronomers deem overwhelming evidence, advocates of the steady-state concept have once again made desperate attempts to salvage their idea. They claim that background radiation results from a huge number of radio emitters that are too feeble to be detected separately. This strategy necessitates the existence of around 100 trillion such sources, nearly 10,000 times the number of observed galaxies, that are 1/1,000,000th as luminous as the radio sources humans do observe. Only a small number of cosmologists are ready to go to such lengths to save the steady-state paradigm. Another criticism of the steady-state model is that it contradicts one of physics' fundamental rules as presently implied. The law of conservation of matter and energy asserts that while both can change shapes, the total amount of matter and energy in the cosmos must stay unchanged. It cannot be generated or eliminated in any way. In contradiction of this law, the steady-state model postulates a constant generation of matter. On the other hand, laws of science are based on scientific data and are susceptible to change dependent on experimental outputs, and not on a human whim. In the steady-state approach, the rate at which matter is generated is so slow that one would have skipped it. Consequently, people would not have uncovered any conditions under which matter may be triggered, or any necessary changes to this law can construe through experimentation. Was there ever a case to be made for the steady-state model? The rough predictor of the universe's age in the framework of the Big Bang scenario was around 2 billion years when the steady-state model was originally proposed. Conversely, the planet and solar system are around 5 billion years old. Besides, the galaxy's earliest stars are at least 10 to 12 billion years old. The obvious difficulty with these age estimations is that the cosmos is younger than the particles it contains. This issue is no longer so critical. The age of the universe is currently projected to be anywhere between 10 and 20 billion years old. The difficulty persists at the lower end of this juncture, but the upper end of the range yields a universe old enough to hold the ancient objects scientists have discovered thus far. The universe has always existed under the steady-state theory. Hence, the age of elements in the universe should pose no concerns. Some people prefer the steady-state assumption to the Big Bang theory for philosophical or aesthetic factors. Some individuals side with the Big Bang theory for emotional or theological reasons, because it includes a moment of creation. Those who disagree with this viewpoint frequently embrace the steady-state model. They prefer the great sweep of a cosmos that has always existed and had a beginning and, by extension, may also have an end in the long run. Several contemporary astronomers believe the steady-state model is erroneous due to a load of evidence against it. The steady-state paradigm, to be precise, continues to be a major intellectual pursuit and a critical component of the annals of 20th century cosmological growth. Steady-state model of the universe. Some selective suppositions. Is there a point in time when the universe was created, or has it always existed? The steady-state model is a cosmological hypothesis for the universe's genesis, which proposes that the universe has always been there and did not have a phase of creation. The steady-state model was popular in the 1950s and 1960s, but only a few astronomers currently believe it is valid, due to some noticeable observations made in the 1960s. The primary assumption of the steady-state hypothesis is that the universe does not change with time on a big scale. It has always evolved and will continue to exist in much the same manner as it does today. The universe is conversely known to be expanding. The architects of the steady-state model proposed that hydrogen atoms formed out of empty space could hold for this expansion in an immutable world. These newly formed hydrogen atoms were just sufficient to fill in the expansion-induced gaps. The steady-state model is also known as the continuous creation theory, since hydrogen is constantly generated. This hypothesis was very popular for a few decades, but increasing observational evidence led to its extinction in the late 1960s. One of the most devastating knocks to the steady-state theory came with discovering cosmic background radiation in 1965. Cosmological assumptions. The perfect cosmological postulate is a combination of 4 assumptions that underpin the steady-state model. As per the first assumption, physical laws are universal. Because physical equations are identical everywhere in the universe, any scientific research performed under comparable situations will yield the same result in the universal gamut. Secondly, the universe is uniform on a suitably vast spectrum. People believe that the universe has a widespread pattern, such as galaxy clusters. Therefore, all inherent constituents are presumed to be homogeneous only on sizes large enough for even the largest features to average out. Thirdly, one assumes that the cosmos is isotropic, which means that it has no preferred orientation. Finally, the world seems essentially the same at all periods over relatively extended periods. The cosmological principle is made up of the first three assumptions as mentioned. One should not mix it with the perfect cosmological analogy. In short, the cosmological fundamentals state that the universe appears to be substantially the same everywhere. Because humans can't travel to every area in the universe to test the assumption, this idea remains mostly unchecked. The perfect cosmological principle is generated by summing the fourth premise. It says the universe does not transform on a massive scale with time. Subsequently, the universe appears to be the same at all periods and all places within its periphery. The steady-state model's intellectual base is known as the perfect cosmological assumption. The universe does not expand in the steady-state model with the inclusion of the fourth premise. Hence, empirical evidence that the cosmos evolves would be evident in the scope of the steady-state hypothesis. Cosmological observations. Astronomers have performed many observations to test cosmological hypotheses, including both the steady-state and Big Bang models. Some of these cosmological findings are discussed further below. Evolution of the universe. People are looking back in time when they observe the farthest objects in the universe. Because a light year means the distance light travels in a year, if one views a quasar that is 3 billion light years away, it has taken the light 3 billion years to reach the Earth. As a consequence, humans have been observing the quasars for 3 billion years. Quasars, the universe's furthest objects, are assumed to be extraordinarily active nuclei of distant galaxies. 1 billion light-years away are supposed to be the nearest quasar. People don't observe any quasars closer than 1 billion light-years away, implying that they vanished at least 1 billion years ago. With time, the universe has evolved. Quasars existed billions of years ago, but they no longer do. This finding demonstrates that the perfect cosmological principle is erroneous, so the steady-state model is also wrong. However, scientists had not then identified quasars when the steady-state hypothesis and the perfect cosmological principle were first proposed. Expansion of the universe. Edwin Hubble, named after the Hubble Space Telescope, found an interesting trend when calculating distances between galaxies. The farther a galaxy is from the Earth, the faster it moves away. The Hubble law is the name given to this connection. For measuring the speed of retreat, this relationship can be used to calculate distances to other galaxies. More significantly, Hubble figured out what was causing the connection. The universe is growing in size. One can draw some galaxies on an average balloon and blow it up to visualize this expansion. As the balloon expands, one may notice how the galaxies get farther apart. Evaluating the distances between the drawn-in galaxies at the speeds they migrate apart would yield Hubble's law-like correlation. Either the Big Bang or the steady-state theory can account for the expanding universe. The new matter must emerge in the steady-state model to plug the gaps created by the said expansion. Usually, as the cosmos expands and the universe's density diminishes, the average distance between galaxies increases. These evolutionary processes would violate the steady-state theory's core postulate throughout time management. As per the steady-state model, hydrogen atoms emerge from the vacuum of space and merge to form new galaxies. Even in an expanding universe, the average distance between galaxies remains constant because of these newborn galaxies. The Hubble plot also demonstrates that the universe evolves throughout time. The slope of the Hubble plot determines the rate at which the universe is expanding. Even for the distant galaxies, if the universe is not evolving, this slope should remain constant. The calculations are tricky, but the Hubble plot for the furthest galaxies appears to curve upward. In the distant past, the universe was expanding faster, contradicting the steady-state model's claim that the universe is not growing. Cosmic background radiation. Arno Penzias and Robert Wilson were engaged in low-noise, static, microwave antenna study in the mid-1960s when they discovered an unintended cosmic revelation. There was still a tiny noise factor after doing everything feasible to reduce noise sources, including removing breeding pigeons and their trash. Because it was cosmic in origin, the feeble noise did not significantly differ with direction, day, or year. The residual heat from the initial Big Bang, anticipated by believers of the Big Bang theory as early as the 1940s, concluded to be this unique 3K cosmic background radiation. This cosmic background radiation supplied substantial evidence to support the Big Bang theory, because it was a previous prediction of the concept. In a steady-state world, advocates of the steady-state model have failed to explain how this background radiation could occur precisely. The steady-state model suffered its most major setback as a result of cosmic background radiation. For their research, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. The steady-state paradigm had several shortcomings, but it did have certain advantages when it was first introduced. The perfect cosmological principle is the cornerstone of the steady-state model. Following this concept, any evidence that the universe evolves and expands is ample proof that the steady-state model is factually inaccurate. The study of the universe, or cosmology, has undergone remarkable changes in the last century. Edwin Hubble, in 1928, discovered that galaxies were retreating from one another. The incident happened shortly after discovering galaxies, or island universes as they were popularly termed at the time. It indicated that the universe was expanding. The cosmic microwave background radiation, CMBR, the signature of the Big Bang, was subsequently detected by Penzias and Wilson in 1965. The COBE and WMAP satellites have created stunning images of the CMBR, along with its anisotropy. It was eventually responsible for the creation of galaxies. Further, contemporary cosmologists are now aware of the age and chemistry of the universe to the 0.1%. More eminent scientists, notably Einstein, assumed that the universe was non-volatile from ancient times until the notion was defeated in 1928. With his finding that the universe is expanding, Hubble duly shattered this paradigm. However, several cosmologists still maintained that the universe was static even after this revelation. Fred Hoyle and collaborators established the steady-state idea in 1948, wherein galaxies tend to retreat. However, the fresh matter is constantly created in the intervening territory. With the finding of CMBR by Penzias and Wilson, the maiden conclusive evidence for the Big Bang, the Hoyle theory was firmly disproved. There were various issues with the Big Bang model until 1980. To prove a point, the visible universe should not be isotropic. It should not look identical in all directions. It was the exact of the original steady-state model. Another concern was the lack of flatness. Up to now, cosmologists couldn't tell whether the universe would eventually stop expanding and start shrinking, or if it would keep growing indefinitely. If this were the case, the primordial universe's density would have to be extremely close to supercritical. The absence of magnetic monopoles, or isolated north or south magnetic poles, was the third major issue. All of these concerns were overcome by Alan Guth's hypothesis of cosmic inflation, wherein the very primitive cosmos expanded dramatically by a factor of 10 to the 50th power or so in just 10 to the negative 32 power seconds. Though there is no definite proof for inflation, there are compelling physical grounds to believe in it. The discovery of dark energy has been the most significant cosmological achievement in the last decade or beyond. This enigmatic energy, which accounts for roughly 70% of the mass energy in the visible universe, speeds up the universe's rate of expansion. The universe is also made up of 26% unexplained dark matter and only 4% luminous matter. It ideally accounts for the display of visible stars. Nobody knows what dark matter is made of, which can't be seen explicitly. but is surmised from its gravitational effects on galaxies. The entire cosmological principle is the foundation of the steady-state model of the universe. Consequently, any indication that the universe evolves is an ample proof that the steady-state paradigm is false. To see if these variants within time average out, one needs to explore even greater periods.